Yeah, I guess we can start. So good morning, everyone, or afternoon, and welcome to this first lecture of the theory lectures by young researchers organized by the Galileo Galilei Institute here in Arcetri, Florence. And today I have the pleasure to introduce Suvajit Majumder, who will address the theme of machine learning quantum integrability in these 2-hour lectures. So please, Suvajit, the stage is yours. I look forward to your lecture.
Thanks a lot for inviting me for this opportunity. So I will be talking about work we recently put on archive. I worked on this problem alongside two collaborators, Shailesh Lal in Bimsa, China, and Evgeny Sobko in Saclay, Paris. So we tried to set up a systematic protocol to search for quantum integrable systems, specifically spin chains, and by using neural networks as function approximators for some identifying objects in such systems known as the R-matrices, which can be thought of as scattering matrices of 2-to-2 particles. So I will not assume any background in neural networks. So I will start by discussing some basic elements of neural networks and specifically the kind of neural networks we use in the paper are there's MLP or feed-forward neural networks, multi-layer perceptron or feed-forward neural networks. This is a special, one of the most elementary types of neural networks one starts with, but it's quite useful for the kind of problems that we care about. So then I will discuss the theory of loss functions and how one uses them to actually tune the weights and biases of the network to get the desired outputs. Another element that goes into this process is the optimization algorithm, which I'm currently looking into actually, but in the paper we use a standard optimization. I will briefly comment about that. Then I will jump and discuss a bit about the quantum integrability topic. So what the key ingredients are there. So the main player there is the R matrix, which is, as I said, 2-to-2 scattering, contains the same information as 2-to-2 scattering in case of integrable field theories, but we will restrict ourselves to spin chains, and this would play the same role as that. Then I will briefly spend some time on how the quantum integrability stories develops from the R matrix. So one can construct something called the T operator or the monodromy matrix, and then from there one can actually construct the quantum charges that are in involution with the system Hamiltonian. And then I will introduce the Young-Baxter equation, which will then be implemented as the loss function of the neural network. So Young-Baxter equation constrains your R matrix, and we will use this to constrain the define the loss function, which will in the end give us the R matrix from the neural network. Okay, so that's the basics, and then I will discuss our results. The main one in the paper is reproduction of the known 14 families of R matrices in 2D of relativistic form. So there is a huge set of degeneracies. When I say 2D, I mean 2D spin chains. So spin half particles at each of the site of the spin chain. So something like the Ising model. So there are 14 known classes. The classification problem is complete there under the quotient of this huge set of degeneracies, and we managed to reproduce all of the 14 families with quite good accuracies. So I will review those, not review, I will state those results, and then I will discuss the kind of search program that we have set up. There are three main parts of it. So there is a general search for integrable models in the space of generic Hamiltonians, and then we actually have something called a repulsion protocol, where we start from a learned model and try to look for new models in the vicinity of that model. And then we will discuss a proposal which should extend to higher dimensions where such classifications are not known. When I say higher dimension, again, I mean the higher dimension in the local spin chain site, so spin 1 and higher spin particles, or higher spin groups, so SUN. So that's the general outline, and also I will, if time permits, I will discuss some of the new results that we have not presented in the paper but are currently generating in 3D and higher dimensions. Okay, so let's begin. So first, what is the setup of neural network that we will be working with? So neural network is a bunch of, it's a function approximator. So you are trying to approximate a function of the input, X input, by dialing certain hidden parameters, which I will be calling theta. And the function f is the output. So, and the way we usually, so the MLP structure, I will use this as the example to describe this neural networks in general. So you have certain neurons in hidden layers. So say we have, the simplest case is a hidden single hidden layer. So depth equals 1, and say we have an output, and this is a fully connected layer. So you have an input here, X in, and this is F out, and you have mid. So here the theta parameters show up. So here you have theta 1, theta 2, theta 3, and the way you are supposed to pass through the network goes something like this, that at any given layer you have, so theta I consists of weights and biases, and the way you act is, and then there is a notion of an activation function as well. So sigma activation, and the way you pass through the network is, at any given layer you define a layer equals, so maybe do it something like this, the output at layer n is you take the input from, so say you are looking at layer n and the ith neuron. So maybe not use theta because theta is the parameter. So let me write them as A1, A2, A3 as the functions at these nodes. So AI n, where in n is the depth, is defined in terms of the neurons in the previous layer node. AI n minus 1, those are the outputs of the previous node. You act with weights of your current node. So that's weights at the current node, so Wi plus bias, and you act with the activation function. This is the activation function. So it's a linear operation on the previous nodes. So here when you are acting on, so to find A1, you use the weight and bias that is currently on this node and operate linearly on Xin to get A1. And then you basically, when you go to the next layer, if there is multiple connections, you sum over those. So that's the protocol. So in this explicit model, what would be F out be? F out will be sum over I plus 1 to 3, the sigma over weights at the ith side times X input plus biases. And yeah, you can have a, so that would be the AI, and then you are using a weight. So this is say weight I1, weight I, bias I1, and you have a weight and bias for each of these. So say weight and bias for each of these nodes as well. So on the output, so you then act with those. So W2 J equals 1 to 3 plus BJ. And yeah, usually you don't have an activation on the output. So this would be your net output. So it's a simple linear plus nonlinear transformations. And you tune these W's and B's to change your function F. And you can search a big enough space if you have enough neurons in the middle layers. So that's the general idea. Okay, so that's an MLP. So what is the specific thing about multilinear perceptron? It says that you connect every neuron you have with every neuron in the previous layer. So you connect, so this is dense network. So you are using, so if you have say 2 layers and an input and an output, you connect each of the neurons of a previous layer with each of the neurons of the forward layer. So this is the structure we use. And each of the connections will have a weight and a bias corresponding to that. For our specific problem, as we will see later, we use depth 2, and the size of the network is 64 neurons at each layer. So, so this width is 64. That's the architecture. So this is called the NN architecture. So that's the architecture we use for our setup. Okay, and regarding the activation function, sigma, that introduces nonlinearity into the problem. Some common activations. So the desired functions are ones where you can actually, means you want a bunch of properties for the function so that when you stack them, these nonlinear functions one after another, the learning is stable in some sense. So the statistics of the function is well behaved. It doesn't blow up or blow down. So some functions that satisfy such properties is tanh activation, ReLU activation. These are 2 of the most popular ones. And for classification problem, it's a sigmoid. So all of these functions satisfy the desired properties, but yeah, in general, these are the common ones. The one that we use was actually recently introduced. So this is a swish activation, and this was recently introduced by Google Brain, and seems to perform better on regression problems, the kind of problems that we care about. And we also saw in practice that this actually is a improvement on all of the standard ones on our specific models. So let me quickly show the activation, the function itself.
Yeah. Excuse me.
Yeah.
I wonder if you just use those functions, is it enough to obtain all these kind of elliptic solutions?
Yeah, so that's the nice thing. So the point is that if you are not, so the kind of functions you can approximate with any given type of activation is generally restricted if you are using a single depth network. But this function space enlarges a lot when you, so there are universal approximation theorems that say that any of these activations would be good enough to approximate any kind of function within a compact domain, given you have considered enough number of neurons. So such theorems exist, and that is the kind of theorem that is one of the constraints on the choice of the function. But we don't really consider that, means we saw experimentally that swish was good enough to obtain the target functions, which includes elliptic functions, as Jacobi elliptic functions as well, because XYZ model has elliptic functions there. So we do manage to get good accuracies within compact domains for those using swish. So it's not this individual function, though a priori looking at the individual activations, it might seem that it shouldn't be able to do that. But because you are stacking multiple layers, the general features of such learning, means like the statistics allow for you to approximate reasonably well. It's quite well actually. So whatever function you are looking for.
Okay, thanks.
So for swish, the activation is just z times sigma z, where sigma z is 1 by 1 over e to the power minus z. Yeah, it's quite funny how they actually, not funny, it's quite instructive how the CS community actually comes up with these functions. They care about, means the statistical properties of these functions when you stack them rather than the individual functions themselves. So that's why they, it's quite interesting that some of the functions that we would expect. So for instance, polynomial functions are notoriously bad at training things because of their statistical properties being blowing up when you stack them. So that's something that we are actually currently looking into, whether we can actually make it work, because we would like to, in general, if you are looking for say holomorphic functions, you would want to have the nonlinear functions, starting functions to be those type only. So because this will in general have poles on the complex plane. So we are trying to actually make holomorphic functions work, but the CS community never look into those precisely because of the those functions don't satisfy the statistical properties of stacking that these standard options do. So yeah, it's quite interesting how they actually come up with these ideas. Anyways, so continuing. So yeah, now let us look at the loss function. So in general, for the most popular problems in CS, means the most popular problems are supervised learnings tasks. And there you are the popular class of these loss functions. So the loss function is the function that you use to optimize your parameters, right? So you have a lot of these tunable parameters, theta I equals weight I and biases, and you want to tune them to get your desired function. And the loss function basically is used to tune these at each step. So you compute the loss and you do a gradient descent on the loss function. And so the loss looks something like this. So if you have, say, f of x comma theta minus the target function, say it is y target of x, and you use some sort of a norm. So L of x comma y comma theta comma y. So you usually use an L1 or L2 norm or Ln in general. So the L1 norm is called mean absolute error. L2 norm is mean square error. And then you have a bunch of relative norms you can use as well, something like divided by the y target of x. If y is regular, then that becomes relative error. And you can use any of these to tune your weights and biases. And how do you do that? So this is when you have a target y function. In the kind of models we are looking at, this is not available to us, right? This we don't know. So in such a case scenario, the kind of loss functions you use is a bit different. And this actually there is a nice set of works. Means we were agnostic about this in the beginning, but a good guideline is the so-called PINS networks, physics informed neural networks, I think. And there they actually use neural networks to solve partial differential equations, and they use the loss function as the PDE. So it means in inspiration, this is pretty much the same as what we are doing. So they have a PDE in the loss, and they try to use the loss to optimize to find target solutions to the PDE of f equals 0. So they're trying to solve this by putting the PDE into the loss. Now, in our case, we don't have PDE, but the Yang-Baxter equation, which is a functional equation. And we actually will be inserting the functional Yang-Baxter equation here instead of a PDE. So in spirit, it's quite similar to how pins work. Okay, so that's optimization protocol. That was loss functions. Now we look at the optimization protocol. How do we tune the weights and biases? So that for this, we use something called backprop. So what does this refer to? So here we actually compute. So backprop is updating your weights and biases. So updating your theta by computing the gradient with respect to theta of your loss, and updating by some proportionality factor of that. So this eta is called learning rate. This decides how much jump you do in your loss landscape. So if it is big, then you are jumping quite far from your starting current point. And if it is big, then if it is small, then you are moving slowly away from your current point. If it is big, then you are moving quite far. So this is something that you need to fix during your runs. And this is called a hyperparameter because you can't tune it using your data. It's fixed using trial and error. So this is doing it this way. It's called gradient descent. So a version of it, one of the first machine learning protocols was the stochastic gradient descent, where this kind of update equations were used. Nowadays, the most stable way to go means there are a lot of options, but the most common one is Adam, which bypasses some of the issues of the stochastic gradient descent. Here, what you do is you actually keep updating the eta based on the history of the loss function. So if you are reaching a saddle point, then because of the loss function being quite stable in the previous iterations, you make your eta lower or make your eta bigger depending on where you are, so that you can have better convergences. So it keeps track of prior loss history. There are some other options as well, RMS prop, but Adam is the one that we also use in our paper, and AdaGrad. And even there is a minimal extension of SGD called SGTM. So where you introduce conjugate momenta to these theta i's, and that essentially does something similar. So it keeps track of the past loss. Okay. So means Adam is the most popular one, and we do use it. Right now I'm actually looking at modification of this whole set of optimization algorithms that was proposed by Eva Silverstein and Bruno at Stanford, they came up with an alternate proposal for optimization using something called energy conserving dynamics, where they view this way of going down the loss landscape as being friction dominated, because your velocity del theta is somewhat like velocity, discrete velocity, and sorry, no, the gradient is a discrete velocity and your update is happening according to the velocity. So it's supposedly can be viewed as a friction dominated motion, but what they do is they define some energy functional and use constant energy orbits to go down, and they show that it can sometimes outperform all of these standard protocols. We are actually trying to see if it does the same in our situation as well. It has some benefits over the standard ones. Okay, so that's optimization. Any questions? So this wraps up the neural network introduction. If not, then we will go into the quantum integrability intro.
Sorry, Suvajit, I see that your battery is running out.
Yeah.
Maybe.
Yeah, 1 sec, let's see. Thanks for pointing there.
Just so it doesn't turn off as you speak.
Yeah. So, yeah, let's discuss briefly what the key ingredients that are pertinent for our discussion in quantum integrability is. So, you start from a spin chain with each side in some representation of the symmetry algebra, and you tensor. The Hilbert space is a tensor over yeah, I think it's better. I equals 1 to L. Product I equals 1 to L. The Hilbert space is a tensor product over your vector spaces, local vector spaces. Now, the R matrix is an intertwiner of two of the local sites. So R, I plus 1 intertwines. So it's an endomorphism from Vi plus 1 to Vi plus 1. So yeah, that's the definition. And you can relate this object. So this object also not only intertwines, but also takes a parameter. So it intertwines them, but also has a continuous parameter dependence. And the way the integrability story works is that you have certain constraints. So there exists an R such that it satisfies a bunch of properties. So first of all, R. So I will just ignore the suffix indices in general. Then R of U equals 0 should be permutation times the Hamiltonian. This is a two-particle Hamiltonian, so H2. And so locally at U equals 0, the R matrix contains the system Hamiltonian information. And furthermore, it satisfies a non-local algebraic set of relations. RU, R12, R13, V, R23, U minus V, R12, R13, 23, U minus V equals R23, R13, R12, U minus V, V, U. Let me just check that I use the correct.
Yes,
minus
sorry,
V.
I don't think it should be U minus V, U and V, right?
Yeah. I always confuse this.
Could I ask a question here? Because I mean, the R matrix might not be regular, namely,
Yeah. We are looking
yeah.
into the restricted setting of regular ones.
Yeah, okay, and also you restrict yourself to the one with, of difference form.
Yes, difference form. Yes. We are currently
But
actually extending these results to non-difference form as well. And non-regular, I'm not sure we can search using integral means neural networks, but the non-difference form, definitely we have some results there as well.
yeah, so but there's another thing, which is you might have I mean, there might be a RLL relation.
Yes.
So basically the Lux operator might not be the same as the intertwiner.
Yes.
Is it possible to also search for those solutions?
Yes, we are actually extending this RRR to RLL, so and also to boundary and Baxter. Actually, we are looking into those extensions right now.
Yeah. So in terms of the machine learning scheme, shouldn't be any problem, right?
No,
probably...
that's a good thing. So we are already have some results for boundary and Baxter. So means that's the nice thing, that this thing generalizes very well to a lot of quite different things.
Okay, yeah, thanks.
Okay, so this algebraic constraint should be satisfied by the R matrix, and basically you can view this as say if R matrix is a 4x4 operator. So if it's a spin-half particle, then the R matrix acts on two spin-half sides. So that means it's a tensor. So it's a qubit to qubit transformation. So sorry, 2-qubit to 2-qubit transformation, and because of that you have a 4x4 R matrix, and when you write these equations you are acting with R matrices that act on two of the three sides, so 1, 2, 3 level 3 sides, and so these are essentially acting on as identity on the third side. So you should be thinking of this as why okay, yeah, charging is happening slower than the decay. Okay, so and this is 8x8. So basically these are 8x8 matrix equations dependent on two complex parameters U and V. So provided you have a solution to the R matrix, you can identify the corresponding Hamiltonian as being integrable, and then you can actually construct the commuting charge set of charges on top of the Hamiltonian. So in the nice thing is that because you have this R of U equals 0 equals the Hamiltonian, a two-particle Hamiltonian, the system Hamiltonian, the spin chain Hamiltonian actually turns out to be sum over the two-particle Hamiltonians at each side. So I plus 1, I equals 1 to L, that becomes the Q2. So the first conserved charge. And the higher charges can be computed by constructing something called the monodromy matrix. So how do you do that? You stack a bunch of these R matrices. So let's say R10, R20, R30, R L0, where 0 is an auxiliary site. And you stack a bunch of these to get your T matrix. So this is an operator that acts on your spin chain plus an auxiliary site. So if you take the auxiliary site to be in the same representation as your local sites, then this would be an operator of size 2 to the power L plus 1 to 2 to the power L plus 1. So this is a big matrix, and you can use this to construct the higher charges Qn. So ddu of log of du dn, yeah. So nth derivative, I think n minus 1. Yeah, sorry, Q2 is the first derivative. So dn minus 1 gives you the higher charges. And there is a property that for a system that has the R matrix satisfying the Yang-Baxter, you can prove that du, tv at different values of u and v commute. And because of this, you get, if you expand it, Taylor expand this in u and v, you get that qm, qn commute as well. So this T matrix actually encodes all your charges, conserved charges, qn. So that's how the story goes. So if you can find an R matrix satisfying the Yang-Baxter equation, then you can essentially go ahead and construct the T matrix and thus such set of commuting charges corresponding to your integrable system. So we will be targeting the Yang-Baxter equation as the loss function for our optimization problem. Okay. Any questions here? I'm a bit worried about the charging situation as well. It's going down faster than it is charging. Okay, so let's look at the setup of the problem then. So we use the setup.
Yes, sorry, could I ask another probably unrelated question, but so here you're kind of discussing about vertex-like models.
Yeah.
Could you do the phase type models? I guess you can. I mean, it doesn't change much, but just
the generalizations means should be possible. That changes the index structure, I think, but shouldn't change the actual structure of the constraints. So it should be possible. We are actually thinking of this is a future direction we are looking into. Generalized Yang-Baxter equations. They somehow take the structure of the so these are some objects that we noticed show up in quantum computing. They extend the they think of the Yang-Baxter equation as sort of braiding matrices. The R matrices are braiding matrices, and then try to generalize that. So constant versions of the R matrices in some sense, but so to higher index objects. And I think we are targeting to actually reproduce these. And phase type would be actually an easier generalization than these objects, but should be possible.
Okay. And probably you can also do like 3D. I mean, I'm not talking about your local dimension. I'm talking
tetrahedral
about like
equations,
tetrahedral or something.
We are thinking about that as well.
Okay. I mean the problem is probably not to just to finding solutions, but to kind of characterize them, right?
Exactly. That's the issue that we are facing. So that's why we are trying to gain as much control in a setting that we understand very well, and then try to so in 4x4 we benchmarked our results and trying to fine-tune our protocols as best as we can, and before going to unknown spaces. So even in local dimensional so 9x9 matrices, we are actually struggling quite a bit to find a good benchmark. So there is a certain subclass of solutions that are known. So we are trying to start from those to extend beyond the known paradigm. Because if we are to make analytic predictions, then we need a lot more control over the unknown space and the behavior of the protocol. So we are currently working on trying to fine tune it in this three-dimensional case before trying to go much beyond that. I mean, in spaces where there is analytic classification or known solutions, it's much easier to actually benchmark those and start from those. but in completely unknown spaces, it's because we are approximating the solutions. So it's unclear. Yeah.
Sorry, what do you mean approximating? So you're not really getting a function that, for example, I mean, if you're interested in, let's say, the elliptic solutions, you will get a series of some.
So we are getting a function f theta x that is spit out by the network, which is close to y of target, right? Whatever a solution is.
So it's kind of a series,
no, it's not even a series. It's actually a numerical approximation that is very well matching with the actual function within some compact domain. So generalizing it beyond the training domain. So right now we are working with something like -1 to 1 or -2 to 2. Generalizing it beyond that is a separate problem that we are also looking into. Symbolic.
Yeah, but suppose that you do not know what you're targeting at.
Yes.
I mean, of course, in the case of the two, local dimension of 2, probably we know. But suppose that you are looking at something that we have never solved before.
Yeah.
How could you guess this function? I mean,
yes. So it has to be. I mean, that's the thing. So targeting. So there are certain technologies available for that. So one of the main ones is symbolic regression. You assume that your function lies within some subclass. So say your function can be built from exponentials and polynomials or something like that. Start from something like that and then try to, it's some sort of a regression protocol. So you try to fit your obtained numerical solution to a high enough accuracies using this. This is another neural network basically. Use this to actually try to predict the corresponding function. We have managed to actually in the 4x4 cases get very reasonably good accuracies of the analytic expressions from our numerical solutions. But again, this is something that we are developing for the specific case we have right now. So yeah, it's work in progress. So symbolic regression is one way. The other way is to actually use the approximation as a starting point and sort of assist, means try to make predictions of what sort of analytic formula it should be and get halfway there and use analytic methods to get the final solution, or some means you need alternate means somehow to. So yeah, these are things that we are actually trying to develop right now.
Yeah, okay, thanks.
Okay, so yeah, so one thing to be very clear about right now, as was pointed out from this discussion, that our solution to the Young-Baxter will be approximation, very good approximation in the compact domain to the scale of 99.99% relative error, relative accuracy. So we have attained very good accuracies, but still these are numerical. So in order to go from them to analytic predictions is a step that takes quite a bit of work, and we are currently trying to develop that. Okay, so what is the setting? So we have the R matrix entries R, I, J, U, and each of these matrix entries, so you can think of this as I plus 1, not Ij, I plus 1, U. So this is a 4x4 matrix if we are using spin half particles. So spin up, 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 down, down, up, down, down is the Hilbert space in, and you have a similar out space, so 4x4, and we are using one of these neural networks. So input U, a 64 with, this was all tuned to optimize this percentage. So this was all experimental. 64 with depth 2. So another layer of 64 with completely connected, and then output. And this output is the this some jkth element. So rjk equals rjk of u. So this is a single entry of the R matrix. and we have a bunch of these kind of networks for each of the output and matrix entries. Okay, so we have a bunch of these networks, and all of them are optimized using the loss function, that is the Yang-Baxter equation, simultaneously optimized. So it's a bit tricky to implement this as a condition because it acts on non-locally. So you need U and V, two inputs, and yeah, 3 copies of the R matrix. So what we do is we have our model, which is a bunch of these 64 times 64 or 64 by 2 network, say 16 of those in the worst case scenario. And we copy the weights and biases, so the theta parameters. We copy from each of these network and then create 3 of those copies. So you have an NN1, NN2, NN3. One takes the input U, the other takes the input V, the third takes the input U minus V. And then we compute the loss and update each of these 3. But the point is that these are not really different networks because they share the same theta weights and biases. But we need the individual U, V, and U minus V to compute this loss. So we generate 3 copies before doing this. So it's a bit subtle, unlike some of the other standard architectures, but not very different. So this is just decided by the loss. So this took us some time to actually figure out how to do this, but yeah, it's quite a fun generalization of standard protocols. Okay, so you do this and then you optimize for the loss. For one thing, so when we started out, we were trying to do something simple like the XXZ model. So we set a bunch of the R matrix entries to 0. So R is taken to be an ansatz like this, D, E, F. Everything else is 0. So then you need 6 networks of this 64 times 2 for each of these non-zero entries. So instead of 16, you have 6. So there is a truncation. And you look for such solutions. And you get the XXZ and generalized XXZ. So it's not quite, you can get XXZ. So these are trigonometric functions. So yeah, generalized XXZ. So there are 2 classes of models here. One is, so you can use the Hamiltonian to classify this. And there are 2 classes of integrable Hamiltonians. One is when A1, A2, B, C, D, E, then A1 equals A2 and A1 plus A2 equals C plus B plus E. These are 2 classes of Hamiltonians, and we do see such a separation of 2 distinct classes of solutions by doing some unsupervised learning on the solution classes. Okay, so yeah, I'm not sure I don't know why the iPad seems to be charging down still. I might have to resort to screen sharing on my laptop after this. Okay, so whenever it switches off, I will switch to my laptop, but then I can't use the notepad. Anyway, so going back, so we have discussed the basics, and so there are 14 classes of families of solutions. Actually, I can switch to the laptop already because it's much easier to actually show the 14 classes. Yeah, I will switch to the laptop and to the paper and discuss from there, I think. Yeah, I might want to keep the rest of the charge in case I want to discuss some of the neural network protocol. Okay, so let's see. So let me. So let's stop the screen share here. Okay, it is already stopped. And share the screen here. Okay, so let's see, how do I switch out of this? And yeah, okay. So so there are 14 classes of solutions, and I review them in the appendix of this paper actually. So these are the so I will just quickly show this 14 classes. And so the way you organize the solutions to the Young-Baxter in this 4x4 setting into these classes is by gauging some symmetry group. And these symmetries include parity, discrete symmetry, and local transformations at the spin half site. So you can rearrange your spin basis at each of the local sites, and that shouldn't change your physical system or doesn't change your spectrum. So you gauge out these degrees of freedom, and then you end up with these 14 classes. And there are two classes of solutions you get for the 6-vertex model I showed. One is where A1 equals A1, so A1, A1, so 6V1 here. And the other one is where A1 plus A2 equals B1 plus B2. So the appendix actually shows all the corresponding analytic solutions. These are all well known. And basically, we targeted this specific Hamiltonian form. So we added another loss function where the function at R matrix at U equals 0 was constrained to be equal to the permutation operator. So that's the second constraint aside from Young-Baxter that we impose, and that forces us to look for the corresponding system Hamiltonian. And doing this, we actually collapse on the corresponding R matrix with very good accuracy. So the dotted line in these pictures are the predictions, and the solid lines are the analytic functions. And as you can see that this is the actual function, and these are the errors. And so the functions range from order 1 values, and the errors are order 0.001. So they are quite well under control in this -1 to 1 domain. And we actually managed to generalize this to bigger domains as well by increasing the network sizes. Okay, so so we show the results working for each of the 14 families. So there is 2 classes of solutions for 6-vertex models of this type, A4. And there are 2 classes of solutions of 7-vertex models, 7V1, 7V2, and there are 8-vertex models where, so the only different type of functions appear in these 8-vertex models, where you have the Jacobi elliptic functions, which were pointed out earlier. And it was quite surprising to see that we could, okay, I will comment about this later, but we do get good accuracies for these classes of models, the same level of accuracy as the others for these classes of models as well. So in 8-vertex, there are 3, 8V1, 8V2, and 8V3. And so these are sort of the standard XXZ and XYZ models and their generalizations. Then there are some funny models, 6 of those. So there is 4-vertex, 2 6-vertex, 2 7-vertex, and 3 8-vertex. So that's 8. And then there are 6 non-XYZ type models that look like this, A19. These are funny in that some of them are singular, some are upper triangular, a bit different from the XYZ, which are basically somewhat more symmetric in the Hamiltonian structure. So these 6 classes have a bit of different functions that for the analytic solutions, they are exponential and polynomial combinations. And yeah, we do get similar accuracies for them as well. So these are the plots for the non-X. So we call them non-XYZ model, but they're just a bit different type of models. Yeah, there are the accurate plots of the predicted versus actual for these non-XYZ type models. So there are 6 of these. Okay, so now what's the protocol that we use to find this model? So there are a few different options for that that we saw were working quite well. And also there I would like to comment on the integrability versus non-integrability perspective. So it's important to understand that because the solution is approximate, what's the guarantee that if you are targeting a particular Hamiltonian, so there is a given a Hamiltonian, if it is non-integrable, we might find an approximate solution even in that case, right? So what's the guarantee that what we are finding is actually a solution if we are using a specific Hamiltonian in that Hamiltonian loss term? So so that's why the suggestion we have in this paper is that don't try to look for a specific Hamiltonian when you are trying to find new models. So using it as a classification for whether a Hamiltonian is integrable or not is not a good idea, because it's relative. The loss values would be quite similar for both integrable and non-integrable models. However, what is nice is if you don't specify a Hamiltonian and just search blindly for models, you always end up on integrable models. So that's something that is quite nice. So we suggest that you go to a model that you know to be integrable, or look for a model without specifying a Hamiltonian first. And once you have landed on one, then you can do a bunch of different things. And that's the discussion that we have. So first we do a general search, find an integrable model, and then you can do something called repulsion. So what that means is that you switch on a loss function, a new loss function that basically kicks you away from, so yeah, this explorer business. So you switch on a loss function that kicks you away from the Hamiltonian that you have just found. You do that by adding an loss term, which is exponential of your current Hamiltonian minus the Hamiltonian that you are trying to repel from. So your training Hamiltonian minus the Hamiltonian. By Hamiltonian, I mean just the derivative of the R matrix at 0. So sorry, I think I mixed two things. The Hamiltonian at 0 is the derivative of the R matrix at 0. The R matrix at 0 is supposed to be the permutation operator. So there are two conditions there. One is regularity and the other is the system Hamiltonian. So when you have found a solution, you try to kick away from that by this thing called repulsion, that we call repulsion, where basically you turn on an exponential loss term, and basically what that does is forces you to move away from the Hamiltonian that you have found. And once you have done that, then you switch that off, and then you again flow to some solution and then do repeat. And this way you can find a bunch of integrable models without being worried about landing on something that is not integrable. So that's the repulsion protocol that we define. And then there is the attraction protocol, where if you know a Hamiltonian is integrable, you can find the corresponding R matrix by using that explicitly as a extra loss function. So these are two different methods, repulsion and attraction, that we suggest. And then we have a explorer scheme, which is basically trying to map out all the integrable models within a setting. So the way we do this, we show a toy model example of this, that we restrict to the class of 6 vertex models. So starting from a Hamiltonian, that is, where is it? I think yeah, so basically that A, B, C, D, E, F that I showed earlier. Sorry, 6 here. Let me just show the 6-vertex Hamiltonian. So yeah, start from a Hamiltonian like this. Set D1 equals D2 equals 0. And so the R matrix will also be 6-vertex type, A, B, C, D. So A1, B1, C1, C2, B2, A2. So these entries are the only non-zero entries. So you have 6 of those networks. And then you search for random models. So you find a model, get to a certain amount of accuracy. And once you get there, so we then repel away from there. And this way, we map all the found models. And then what we did was we clustered them. So that's unsupervised learning. So what we do is you map the Hamiltonians in some high dimensional space. So this is basically we map them in the components. So basically that's 6 complex numbers. So that's 12 dimensional vector space. So the Hamiltonians were mapped as vectors, and then you try to cluster them, which is basically way to and we specified that try to cluster them into 2 classes. So put them into 2 classes based on their neighborness under certain metric in this 12-dimensional vector space. When you do that, we notice that you get extremely high accuracy of their clustering based on the corresponding integrable class. So there are 2 classes of integrable models that we know exists in these 6-vertex models, and using the clustering algorithm, we managed to get the 100% accuracy almost for these 2 classes. So basically, this was a sort of check of the idea that in an unknown space, once we have done a dense enough search for integrable models using the clustering algorithm, any clustering algorithm, we should be able to identify the equivalence classes of solutions in a reasonable way. We have not presented it in this paper, but we have actually managed to extend this work to the 14 classes of solutions that exist here. So it seems to be reasonably robust in the well-explored space of these relativistic models in 4x4. So this is our proposal for how to extend this, use this methodology to extend to higher dimensional cases where the analytics classification program is not under control. So that's the main proposal that we have. And okay, then in the future directions, we basically outline a bunch of different things that we are currently working on. One of them is this looking at holomorphic networks, because so our training protocol was within a real line. So there is this problem that our neural networks are quite well explored on input that is real. However, when you go to complex inputs and try to upgrade your weights and biases to complex numbers, things are not that well explored in the computer science community. So we are trying to, we have managed to actually work out a proposal of how to view these functions in the complex plane in a meaningful way, or how to extend this. So how to analytically continue these solutions that we have to the complex plane. Because at the end of the day, the most general integrable field theories have nice analytic structures in the complex plane, which we would like to explore. For instance, the poles of the corresponding S matrix. So the integrable field theories, the R matrix is the same as an S matrix, and then you have Young-Baxter equation for the S matrix, and the S222 S matrix contains the information of bound states. So the non-local properties like branch cuts and all contain information about the bound state. So we are currently seeing how to extend this formalism to the complex plane and incorporate such singular structures. There are works that show that such a thing should be possible. There is a work that came out last year on differential forms, trying to learn differential forms with certain special properties, and they managed to actually capture information about poles and zeros of such functions. So we are hoping to actually do something similar, but with the S matrices, and try to incorporate the singular and zeros and poles, basically branch cuts and zeros and poles of meromorphic functions. Yeah, by starting from a solution on the real line. So that's something that we are trying to work out right now. But the problem there is that in order to actually go to the complex plane, you would ideally want to have the poles under control, for which we want to be actually working with regular solutions on the complex plane. But somehow when so there are two approaches. One is to actually start with a real solution and try to extend it to the complex plane, and the other is to try to learn the function in the complex plane itself. Trying to learn in the complex plane seems to be somehow not very well behaved, in that the Young-Baxter equation seems to be, the approximations are quite bad. There we have not found a nice way to actually find approximations. So it's not stable, basically. This method of learning is not very stable there. So that doesn't seem to be very well behaved. So we are trying the other way of keeping the real solution as a boundary condition on the solution in the rest of the complex plane. So that's something that we are trying out. Some other things that we are doing, I already mentioned that generalizing to 3D. We have already a lot of numerical solutions, but it's not useful until we make analytic predictions. So we are actually trying to improve the symbolic regression packages out there to make analytic predictions for the functions that we are getting. So we have some nice generalizations of known 15 vertex models in 3D, which seem to be in the same spirit as the XYZ model in 2D, but we are not there at the point where we can make analytic statements from the numerical solutions. Okay, so that's one direction. And also we have actually managed to extend our work to non-difference form in 2D, where you have these nice solutions to the Young-Baxter equation that represent ADS CFT R matrices. So the R matrices that show up in ADS CFT planar limits, specifically ADS3 and ADS5, as well as ADS2. Actually, there are some nice ones there. So we have managed to actually recover those, and currently we are trying to make some conjectures about further solutions, interpolating between those ADS CFT R matrices and beyond. Yeah, and also there is some work that we are trying to do regarding boundary Young-Baxter and generalized Young-Baxter equations. Okay, so I think that's it for the paper. Are there any questions? Sorry for the situation with the iPad. Somehow I should have actually been more careful. Are there any questions on the interview?
Okay, I guess there are no more questions. So
yeah,
let me thank again Suvajit for this nice lecture.
Mm-hmm.
You got a lot of questions along the way, so
yeah,
in the end, you already answered all of them. So thanks a lot again for this lecture, and stay tuned for the next one.
Okay, thanks a lot.
Thanks a lot.